Hello, good morning, dear students. Welcome back to the chemistry class. Yes, in the previous class, we have completed regarding the mechanism of adsorption of reactant molecules on the solid surface. It is in catalysis process, homogeneous and heterogeneous catalysis, and the mechanism of heterogeneous catalysis is explained based upon the model adsorption theory, right? So now in today's class, we'll move to the next concept, that is about enzyme catalysis. Enzyme catalysis. So here, in enzyme catalysis part, just we need to discuss about what is meant by enzyme catalysis, and particularly specific examples for enzymatic catalyzed or enzyme catalyzed reactions, and then mechanism of enzyme catalyzed reaction, and few of the applications we need to mention, right? So after that, we'll move to the next concept, that is about colloids. So let's discuss first regarding enzyme catalysis. Enzyme catalysis. Yes, what is meant by enzyme catalysis? As we know that enzymes is nothing but what? Enzymes are chemically, we can define. Enzymes are chemically, these are the proteins with very large or high molar mass, very high molar mass. Approximately the molar mass of the enzymes, which varies from around 15,000 to 1 million, 10 power 6 grams per mole. The molecular mass of an enzyme, it varies from 15,000 to 10 to the power 6 grams per mole. These are the enzymes are chemically, these are the proteins which its mass is ranging from 15,000 to 10 to the power 6 grams per mole. So very large and having very high molecular mass. Enzymes are the proteins with very high molar mass are called as enzyme. And these enzymes, which are produced in the living system and which catalyzes biochemical reactions, Enzymes definitions. These are the proteins with very high molar mass. These are produced in the living system and which catalyzes biochemical reactions. Now, some specific examples of these enzyme catalyzed reactions. So, different examples are there. Just you can make a table. Enzyme catalyzed reactions. Which enzyme catalyzes a particular reactions? Means reactions can be catalyzed with specific enzymes. So please note that table, that is about enzymatic reactions. One is enzymatic reactions with its enzyme. Which enzyme can catalyze this reaction? So a different number of examples you can find. A different number of examples. Number one, first one is, so here starch or sucrose can be converted into sucrose. Sucrose can be converted into sucrose to glucose and fructose. Glucose plus fructose. This is a reaction which is catalyzed by an enzyme, right? The second example is starch to maltose. maltose. So this is a reactions which is catalyzed by a specific enzymes. This is catalyzed by invertase. Invertase is an enzyme which can catalyze the reaction or conversion of sucrose into glucose plus fructose. This enzymatic reaction can be catalyzed by only invertase. Invertase, yes, invertase. Whereas the second, starch to maltose is is an enzyme which can catalyze this reaction. The third one is maltose can be converted into glucose. This maltose it can further be converted into two molecules of glucose, glucose plus glucose, glucose plus glucose. So these reactions can be converted by maltose into glucose. It is maltase. Maltase. So these are the enzymatic reactions which can be catalyzed by a specific enzymes. So sucrose to glucose plus fructose is catalyzed by invertase, whereas the starch can be converted into maltose by using an enzyme diastase, maltose to glucose by using maltase. The next, glucose can be converted into alcohol. Glucose to ethyl, ethyl alcohol. So this by zymase. Zymase is an enzyme which converts glucose to alcohol, urea to carbon dioxide. Urea can be converted into carbon dioxide plus ammonia by urease. Is an enzyme which converts urea to CO2. Next, proteins are converted into amino acids. Proteins can be converted into amino acids by using an enzyme called pepsin. Lactose can be converted into glucose. Lactose can be converted into glucose plus galactose. Lactose to glucose plus galactose by using an enzyme lactase. Lactase. So these are the different number of examples. Enzyme catalyzed reactions, and these reactions can take place only in the presence of a specific or particular enzyme. So these are the enzymes which can catalyze these reactions. Other than this, no other enzyme can catalyze these reactions. Only a specific enzymes can catalyze a particular reactions. So enzymes are chemically proteins with having very high molar mass, approximately 15,000 to 10 to the power of 6 grams per mole, which are produced in the living system and which catalyzes the biochemical reactions within the living organisms. So these are some examples where sucrose can be converted to glucose and fructose by using an invertase. So particularly, which of the following enzyme can catalyze the reactions from X to Y? I can ask the particular examples. You need to remember this. I think in biology also you might be studied regarding this enzyme catalysis. So now next is, so here regarding the enzymes, what are the characteristic properties of enzymes? The main characteristic properties of the enzymes. So please note these examples. After this, we will go for next characteristics of enzyme catalysis. Characteristics of enzyme catalyst. So note these examples. Next is Characteristics of enzyme catalyst. Characteristics of enzyme catalyst. Characteristics of enzyme catalyst. From these examples, in the characteristics part, we can discuss a very few points which are unique regarding this enzyme catalysis. Or right. So the next is characteristics of enzyme catalysis. So here, as we know that enzymes are highly specific in nature. So here in the characteristic point, the first point is high efficiency. First point regarding its efficiency. High efficiency of enzyme. High efficiency. So here, an enzyme catalyzed reactions are very fast as compared to the uncatalyzed reactions. So the time required to digest one time a food meal, it takes around 50 years in order to digest a one time meal. But due to the presence of biological enzymes, so within 3 to 4 hours, it's going to digest within 3 to 4 hours. So that means enzyme catalyzed reactions are very fast as compared to uncatalyzed reactions. So approximately even 10 to the power of 20, 10 power 8 to 10 power 20 times the rate is increased in the presence of an enzyme catalyst. So here it is highly efficient. So enzyme can catalyze the reaction or it can increase the reaction rate from up to 10 to the power of 8 to 10 power 20 times of an uncatalyzed reaction. So it increases the rate of reaction up to 10 power 20. And even extremely small quantity is required. Small quantity is enough. Small quantity is enough. So small quantity means as small as compared to 1 millionth times of an the quantity of an enzyme is 1 millionth time. That means 1 by 10 power 6. That very extremely small quantity of a catalyst, particularly enzyme catalyst, can catalyze a reaction by 10 power 3 to 10 power 6 times. That means the rate of a reaction is increased by 10 power 3 to 10 power 6 times. Even a small quantity, as small as such as it is 1 by 10 millionth time. So if we use a very small quantity, that is 1 by 10 power 6, 1 millionth times, 1 by millionth times of a quantity if we are using, that means 10 power minus 6 grams per mole. Such a small amount of an enzyme catalyst can catalyze a reaction, can increase the rate of a reaction from 10 power 3 to 10 power 6 times. So 1000 to millionth time the rate is increased very by using a very small amount of an catalyst. So a very extremely small quantity of enzyme is enough to increase the rate of a reaction by 10 power 3 to 10 to the power of 6. And the third one is optimum temperature and optimum pH. Optimum temperature. So here optimum temperature means the catalytic activity of an enzyme becomes maximum at a particular temperature. The temperature is called as optimum temperature. The activity of an enzyme becomes maximum at a particular temperature known as optimum temperature. Means the temperature at which the enzyme show its maximum ability. The rate is increases to the maximum extent at a particular certain temperature. That temperature is called optimum temperature. And usually 25 to 30 degrees Celsius is the optimum temperature, that is 298 Kelvin to 5 degree. Even 310, approximately 310 Kelvin, 298 to 310, 25 to just 30 if you are using plus 273, 303, or you can take 25 to 35 degrees Celsius, 10 degree difference. 298 to next to 308 Kelvin. So roughly we can get 310 Kelvin. So in this, that means 37 exactly on right. So 25 to 35 degrees Celsius, 12 degree difference. So in this temperature range, so enzymes which shows the maximum tendency or maximum activity affect in order to increase the rate. So the enzyme activity, the catalytic activity of the enzymes is maximum between this temperature. So this temperature is called as optimum temperature. The next one is optimum pH. So usually enzymes show the maximum activity at a pH ranges from 5 to 7. If pH of the solution is 5 to 7 or the medium is 5 to 7, then the enzyme activity is very high. Enzyme activity is very high at particular pH known as optimum pH. So here the word optimum pH and optimum temperature is nothing but certain pH and temperature is required or where the activity of enzymes is maximum. That temperature is called optimum temperature and pH is known as optimum pH. Optimum pH. The next one is, so these enzyme catalyzed reactions can be controlled, so it can be regulated or controlled activity of enzymes. So it can be controlled. Activity of catalyzed enzyme catalyzed reactions. Activity of enzyme catalyzed reactions can be controlled and regulated. Can be controlled. Can be controlled and regulated. And is regulated. Controlled and can be regulated. Next, catalytic activity can be increased or decreased, like catalytic activity promoters and poisoners, as we have studied promoters and poisoners. So the activity of a catalyst can be enhanced or it reduced by the presence of other substances. Similarly, in case of enzyme catalyzed reactions also, some of the coenzymes are used which can increase or decreases its activity. So coenzymes means the activity of an enzyme, activity of enzymes is increases by using a coenzymes or it can be reduced. So the activity can be increased or decreased in the presence of some other substances called enzymes, other substances. So these are some important characteristic features of catalyzed. The next is mechanism of enzyme catalyzed reaction. Next one is mechanism. So how an enzyme increases the rate, enzyme catalyzed reactions. Its mechanism. Enzyme catalyzed reaction. So here the mechanism of enzyme catalyzed reactions, which involves two steps. A very simple mechanism. In the first step, the enzyme which combined with the substrate molecules and it forms a complex called enzyme substrate complex, and there it reacts and products are produced. The enzyme substrate complex which gives the product and enzymes as it is in the original form. So enzymes, it remains as it is. So reactants are converted into product. So the mechanisms involves two steps. Usually in step one, enzyme. See, in simple form I am writing enzyme E, which combined with the reactant are called substrate. reactant or substrate. So enzyme combines with the reactant or substrate, which gives rise to enzyme substrate complex. Yes, enzyme substrate complex. That is the first step. Whereas the second step, in step 2, so this enzyme substrate complex are intermediate. This gives rise to enzyme plus product. Enzyme plus product. That means here this is substrate substrate is converted into product. Substrate is converted into product, and enzyme remains as it is. Enzyme remains as it is. So here, as you know that enzymes are highly specific. Only particular enzyme can catalyze a particular reactions, not others. So in the first part I have given some of the examples. A particular reactions can be catalyzed by only a certain particular enzyme, not by others. So it is highly specific. So if enzymes, lock and key model, lock and two mechanisms we can explain. One is lock and key model, and other one is induced fit. Induced fit. So first, usually we are going to explain regarding the lock and key model. So lock and key model particularly. So enzymes. So for example, if this is an enzyme structure of enzymes, so let us consider one something structure, lock and key models. And substrate. So enzymes plus substrate molecules. So substrate. So this is the substrate. So it is an enzyme. This is enzyme, and this one is reactant. That is substrate reactant. So when these two enzymes plus substrate, this gives us to enzyme substrate complex. So just it fits into lock and key models. Lock and key, just it fits into the enzymes and it forms an intermediate. So there is enzyme substrate complex, enzyme substrate complex, and this gives us to the product. Enzyme substrate complex, enzyme substrate complex, and here this substrate is converted into product in this enzyme substrate. So this is converted into a product, and this gives rise to this further it gives rise to I'm writing the direct product on the second step. I also can add one more step separately. So this is in the step 1, whereas in step 2, so that enzyme substrate complex, enzyme substrate complex. So this produces the product. This gives us ES. This is ES, enzyme substrate complex. So this gives us to enzymes back as this is the enzymes plus. So it is converted into product. Two product. And the other one is enzyme substrate so two products are formed. So these are the products. Product, and it is enzyme substrate. So the mechanism of enzyme catalyzed reactions involves only 2 steps. Step 1, the enzymes combines with the substrate. It is the enzyme and the substrate. It just combines, which binds with each other and it forms the enzyme substrate complex. So in this enzyme substrate complex, which gives rise to enzymes as it is back in the original form, plus the substrate is converted into the product. So the reactants to product in the presence of the catalyst. Reactant to product in the presence of. So this is regarding enzyme catalyst. Examples, its characteristic properties and mechanism. The next is one simple definition: shape selective catalyst. Shape selective catalyst. So what is meant by shape selective catalyst? Examples are zeolites. So zeolites are act as a shape selective catalyst. Why? What is meant by this shape selective catalyst? The catalyst which depends upon the pore structure of the catalyst and size of the reactant and product are called as the shape selective catalyst. And here zeolites are the best examples of this kind, shape selective catalyst. So what is meant by shape selective catalyst? The catalyst which depends upon catalysis, the process which depends upon pore structure of the catalyst and size of reactant and product are called as a shape selective catalyst, and examples zeolite. That concept you need to remember. Okay, right. So now let's move to the next concept, that is regarding colloids. So we have completed two concepts. First one is regarding concept of adsorption, and the second is regarding enzymes. Next colloids. So in this part we are going to study about classification, preparations of colloids, purifications of colloids, properties of colloids, and the last is regarding emulsions. Colloids. So what by colloids? Yes, colloids. So in solutions can be classified into two types based upon the particle size. One is true solutions, suspensions, and colloids. True solution, suspension, and colloids based upon the particle size, right? So here, what is meant by true solutions and suspensions, colloids? Can you define these three? And what are the properties, that is distinguishable properties? That means difference points you can write with respect to some of the properties. So as you know that we can differentiate directly between true solutions and suspension. What is meant by true solutions? Yes, and suspension. Suspension means the particles, solute particles are settled down and it is easily visible to the naked eyes. Whereas true solutions, the solute particles is completely mixed up with the solvent and the particles are not visible. It is clear solutions. Whereas this one is turbid. True solutions and suspension. Whereas the colloids are the solutions which lies in between these two. The properties of those colloids which is lies in between true solutions and suspension. So here some of the properties and how we are going to distinguish between these three. That is true solutions. True solutions are also called as crystalloids. True solutions are crystalloids, colloids, and suspension. So you just make 3 columns or 4 columns. In one, first is regarding its properties. The second is regarding those 3 types of solutions. So in the colloids, so particularly before starting this colloids, just regarding the types of solutions. So you make first properties. So what are the properties we are going to discuss? A few properties. So first point is with the true solutions. True solutions. True solutions are crystalloids. Second one is colloids in intermediate, and then suspensions. Suspensions. So properties, true solutions, colloids. So first is particle size. Particle size. We are discussing regarding the particle size in true solutions, colloids, and suspension. The solutions in which, if the particle size is less than 1 nanometer, particle size is very small, less than 1 nanometer, then it is called as true solution. The particle size is less than 1 nanometer. The particle size is less than 1 nanometer. Whereas in suspension, the particle size is greater than 1000 nanometer. 1000 nanometer and 1 to 1000. So here the particle size is in between 1 nanometer to 1000 nanometer. 1 nanometer to 1000 nanometer. The particle size is in between 1 to 1000 nanometer. This is about the size of it. Next one is nature. Nature of solution. How it is homogeneous or heterogeneous. Nature of these 3 solutions. So okay, right. Suspension is it is homogeneous, heterogeneous, heterogeneous. So this one is heterogeneous. It is heterogeneous. Whereas true solution is it is homogeneous. Whereas this colloids, colloids is also it is heterogeneous solution. Homogeneous, heterogeneous, and heterogeneous. One is particle size and its nature. Next, the process of separation. Separation. How we can separate the solute ions? Separation. Separation. So how we can separate the dispersed phase and dispersion medium, that is solute and solvent. So next one is separation of these solutes. So by using filtration, that is ordinary filter paper and ultra filter paper. So can we separate true solutions, solute particles from solvent in true solutions? Is it possible separations of this solution? No, it is not possible either by ordinary filter paper or ultra filter paper. So in this case, separation by ordinary separation by ordinary or ultra filter paper. Ordinary filter paper or ultra filter paper. In both cases, it is not possible. Even ordinary and ultra filter paper you can use, but separations is not possible. Whereas in colloids, in ordinary filter paper, we cannot separate the colloidal solutions. Whereas by using ultra filter paper, we can separate these. By using ultra filtration, we can separate the solute particle from colloidal solution by using ultra filtration. Whereas in suspension, these two can be separated by your ordinary filter paper or as well as ultra filtration method. We can separate. We can separate. So this is regarding the two solutions, colloids and suspension. So first one is its nature, particle size, separation. Next, visibility. Can particle size are visible in this case? In true solution, visibility is not possible. Visibility not possible. Colloids, it is true solutions are not possible even under ultra microscope. Whereas colloids can be visible under ultra microscope, and here it is directly visible by using naked eyes. Visibility. So some of the properties with respect to the solutions we have discussed. Now directly we will discuss about only this part. Colloids, its preparations, its classification of colloids, preparation of colloids, its purification and their properties. Classification, preparation, purification and properties regarding to colloids we are going to study under the heading, separate heading, colloids. So next take the heading colloids and the classification. So how the colloids are classified? Classification. So your colloids can be classified into different types based upon the different properties. So first classification based on the physical state of dp and dm, it is classified into 8 types. First, based on physical state, based on the physical state of dispersed phase and dispersion medium. Dispersed phase, that is nothing but solute, and dispersion medium, solvent. So what is the physical state of solute and solvent? Based upon that, we are going to classify the colloidal solution into 8 types maybe. So here we can make that physical state of dp, dispersed phase and dispersion medium. Type of colloid, this is very important. Type of colloids, and some examples you can example. So here directly the dispersed phase, dispersion medium and type of type of dispersed phase, physical state of solute. It may be solid, liquid, gas, and dispersion medium may be solid, liquid, gas. So first, I am considering here it is solid, liquid, and gas. Dispersion medium is solid, solid, solid. Like in solution topic, we have studied regarding the types of solution. Solid, solute and solvent. If the solvent is solid, it is called solid solutions. And specific types of example. Next, so it may be solid, liquid, gas, and the dispersion medium is liquid, solid, liquid, solid, liquid, and gas. Whereas this is liquid, liquid, and liquid. And the third, solid and liquid, solid, liquid in gas and gas. So gas and gas do not form electrolytes. It's a mixture of gas and gas which do not form. So these are the 8 types of colloids, and which are in particular in solid in solid. If either two dispersed phase or dispersion medium is in solid phase, then it is called solid solid. Solid in solid, solid solid. Here the sol is a short form of solution, solid solution. And the second one, liquid in solid, it is gel. Gas in solid, it is aerosol, aerosol. Solid in liquid, liquid in liquid, gas in liquid, solid in gas, and liquid in gas. So totally 8 types of colloids. You just make a name. What is the name of this colloid, particular colloid? So first one here, solid in solid is solid solid, solid solid, solid solid. Short form of solution, solid solid. The second one is liquid in solid is called as gel. Liquid in solid, and gas in solid is solid. It is again solid. Gas in solid. And one more, gas in solid. Solid in gas is aerosol. So here it is again solid, solid, solid. Gas in solid. Next, solid in liquid. Solid in liquid. It is simply we can call solution. Simply it is called solution. Liquid in liquid, it is called emulsion. Emulsion. Liquid in liquid called emulsion. Liquid in gas, liquid in gas. Solid liquid, liquid in gas. Next one is gas in liquid. Gas in liquid is known as foam. Gas in liquid is called foam. Solid in gas. Solid in gas, aerosol. Aerosol. Next, last, liquid in gas. Liquid in gas is also known as aerosol. Solid in gas, liquid in gas, it is also aerosol. Aerosol. These are the 8 types of colloids. 8 types of colloids. So we can give some of the examples of this type. So particularly, identify the dispersed phase and dispersion medium in any one of the type of colloid they are given us. Name the dispersed phase and dispersion medium in emulsion. So what is the dispersed phase and dispersion medium? Both are in liquid and liquid. Dispersed phase is liquid. Dispersion medium is also liquid. So what is the dispersed phase and dispersion medium? So in aerosol means it is again confusion. So particular example they will give. Particular examples. So identify the dispersed phase and dispersion medium in this. So here please note some of the examples. Solid, solid. That is in solid, solid. Give an example. Generally alloys and colored glasses. So example alloys. Alloys and colored glass. Colored glasses. Next one is liquid in solid. Liquid in solid, that is gel. Jelly, butter, cheese, uh, jelly, butter, cheese, etc. Next, gas in solid. Solid gas in solid. Pumice stone, a particular type pumice stone is an example where the gas is dissolved in solid. It is a solid salt, pumice stone, and foam rubber. Foam rubber. Specific examples of this kind. Next, salt. So for this, you can give number of examples where solid is dissolved in liquid. Because solution topic completely, almost we have studied regarding only one type topic solution. That is solid is dissolved in liquid. Either electrolyte or non-electrolyte, which is dissolved in water. So this kind, so you can give number of examples for this. You can give the number of examples. Next, liquid in liquid, liquid in liquid, milk, hair cream, etc. Milk, emulsion, milk, hair creams, etc. in emulsions. Next, liquid in gas, aerosol, liquid in gas, mist, fog, cloud, etc. That is liquid in gas. Before going to the first one, study gas in liquid, gas in liquid form. So here, soap, leather, foam. Soap, leather, froth is an example. Even soda water, gas in liquid, soda water is an example of this category. Next, solid in gas, smoke, dust, aerosol, smoke, dust, particles, etc. Where the solid particles are dispersed in gas. And the last one, liquid in gas, mist, fog, cloud, mist, fog, cloud, etc. So these are the examples. Particularly how they are going to ask. So identify the dispersed phase and dispersion medium in milk. Even they are not going to say this particular name, emulsions, gel layers, or etc. So identify the dispersed phase and dispersion medium in form. So what is the dispersed phase? Dispersed phase, that is liquid is dispersed in gas, or gas is dispersed in liquid, solid in liquid, or liquid in solid, etc. So the same table, just except this term, we have studied in solution topic. Types of solution: solid, liquid, solid solution, liquid solution, and gaseous solution, with some particular example. So here also this. So this is the first classification, which is based on dispersed phase and dispersion. And two more classifications are there, which based upon the type of dispersed phase particles and the nature of interaction. Based upon the nature of interactions, it is classified into two types: lyophilic and lyophobic. Based upon the type of dispersed phase particles, it is classified into three types: macromolecular, micromolecular, macromolecular, and associated. Three types. So those remaining two classifications and its preparations will continue in the next.